Okay, so the next speaker is Marius Gerbershagen from University. Thank you.
Yeah, first I would like to thank the organizers for putting together this very nice conference and stepping in when the original plans for Eurostrings couldn't get through this year. So I'm going to talk about a project which is ongoing with another PhD student from University, Dongwing He. And the project is on bi-quantum corrections for non-spatial holographic entanglement. And let me first introduce non-spatial entanglement before I get to the bi-quantum correction. So the starting point is a very simple question. So I guess all of you will have heard of the Takanaki formula, which says that the entanglement entropy of a spatial subregion on the ADS boundary is dual to the area of a minimal surface of codimension 2 in the ADS space. However, in many cases, there are not only minimal area surfaces, but there are also many extremal area surfaces which are not minimal. For instance, here I've drawn a picture of a black hole, and there you have an infinite collection of extremal surfaces which wind around the black hole horizon. And then you can ask yourself, okay, if we know that the minimal surface is dual to an entanglement entropy, what about the area of the non-minimal surfaces? Is there also a duality for that? And it turns out in some cases there is, but you have to consider not only entanglement between spatial degrees of freedom, but also between different fields. Before I introduce the exact definition of this non-spatial entanglement, let me first give some motivation why studying non-minimal extremal surfaces is interesting in the first place. So since about 15 years, there has been an idea floating around in ADS-CFT that entanglement should be intimately connected to the ADS geometry, which has been summarized under the slogan entanglement builds geometry. And if you take this idea very seriously, you start to run into a sort of problem, namely that there exist so-called entanglement shadows, certain regions of space-time which are not probed by any real Takanaki surface. So an example is just a one-sided black hole here, where you have this gray region outside of the ADS horizon at a finite distance, which is not probed by any real Takanaki surface. So you can increase the size of the subregion A on the boundary, and you will find that there are surfaces which go just around the entanglement shadow, but no surface will enter. And a very similar thing happens for a two-sided black hole if you consider an area which is split up between the two asymptotic boundaries. So you're looking at correlations between the two asymptotic boundaries. Then if you are at a time region close to the bifurcation surface, then you will find RT surfaces which go through the wormhole from one asymptotic boundary to the other. But as you go up in time, at some point, the real Takanaki surface splits up into two disconnected components, and these lie entirely outside the horizon. So again, there's this region drawn here in gray, where no real Takanaki surface enters. And that's kind of a problem for this entanglement builds geometry idea. However, if we take into account these non-minimal extremal surfaces, then you can simply probe those entanglement shadows directly. They simply enter into those gray shaded regions here. So they can resolve this problem of entanglement shadows. And there's another interesting feature, namely that you can probe much closer to horizons or singularities, and then at least if you go close to a singularity, we would definitely expect large quantum corrections to appear here. So this could potentially tell you a bit more about how entanglement builds geometry works in this situation, and certainly if there is a breakdown of this idea due to the large quantum corrections. So if the classical notion, or the notion of a classical space-time, which is what we mean when we say geometry in this case, if this notion really stops making sense as you go very close to a singularity. And that's the sort of feature you could probe using these minimal extremal surfaces. Now let me go to the definition of what exactly I mean by non-spatial entanglement entropy. So this quantity has also been called entanglement. So I'm going to use this name, although you should keep in mind that this is simply an entanglement entropy. You're just using a different bipartition of your degrees of freedom. And I'm only going to be working in an ADS3CFT2 setup, which is sort of bottom up, in the sense that I'm going to assume that the boundary conformal field tree has the structure of a symmetric product orbifold, but I'm not going to assume anything about the seed conformal field tree. So this means that the action of the theory is simply n copies of some further unspecified conformal field tree plus some marginal deformations that will sort of destroy the exact symmetric product orbifold structure. So it is unclear to me if that is the most general bottom-up ADS3CFT2 picture you can write down, but at least it covers a very large class of systems, for instance, the well-known D1D5 system, or recently it has also been shown that ADS3 cross some arbitrary compact manifold with pure and SNS flux also is described by a boundary CFT that has this structure. So I'm just going to assume that this holds true for the class of models I'm studying. Now, the field content is just indistinguishable copies of the fields from the seed theory, but there's also an important feature that the Hilbert space contains states where the boundary conditions for these fields change. So we're just looking at the seed theory itself. You can only have fields which are periodic or anti-periodic with themselves, but in the symmetric product orbifold, you have boundary conditions that sort of join up together fields by boundary conditions that are symmetric, that are periodic or anti-periodic up to permutations. So for instance, if you have 3 copies, then you can have the simple situation where all of the fields are periodic or anti-periodic with themselves, or you could have a situation where 2 of the fields are joined together by the boundary condition and the other field is separate, or all of the fields are joined together. So these sort of long strands will turn out to be very important. And in particular, if you want to specify some subsystem of this theory, for which you want to compute entanglement entropy, you have to specify how you distribute your subsystem among these strands. And if you do it for the ordinary entanglement entropy, this distribution is very simple. You consider all of the fields in the same subregion. So if you have a long strand which is made up of a certain number of fields, let's call them M fields, then you will have M intervals of the same interval distributed among this long strand. But for this non-spatial entanglement entropy for entanglement, you use a different distribution of subregions among these long strands. Namely, this definition of entanglement is parameterized by 2 integers, one integer w, which will turn out to be the binding number of the dual extremal surface, and another integer m, which is constrained to be larger than this value. And now, if we want to choose some subsystem for the degrees of freedom, for which to compute entanglement entropy for entanglement, what we do is we first only put our subsystem on long strands that are of length, which is an integer multiple of this parameter n. So for instance, here in that case, m is equal to 3, so I'm only considering long strands of length 3, of length 6, of length 9, and so on. And then on these long strands, I put an interval which is greater than 1, so which covers more than one field of the seed theory, or in general, I would put an interval of length w plus f. And if I have a long strand of length 6 here in this example, then I'm going to put 2 intervals. For a long strand of length 9, I'm going to put 3 of those intervals, and so on. And now if you compute the entanglement entropy for this kind of setup explicitly, then you find, using large N techniques, which are relatively standard in 2D CFTs, that this kind of non-spatial entanglement entropy is indeed dual to the length of an extremal surface with non-zero binding number. So as before, you have, as for the ordinary entanglement entropy, the duality relates the entanglement entropy to the length of this extremal but non-minimal surface divided by 4gn, and in that particular case, you also divide by 1 over n, simply because you consider a smaller subset of degrees of freedom, so also your entanglement entropy is smaller. And this has been shown for conical defects and also for BTC cores, which are the 2 most interesting cases for ADS3CFT2. And already in this large n limit, there are interesting effects which appear. Namely, if we consider this 2-sided black hole again, as before, you will find a phase transition. So just as for the ordinary entanglement entropy, also for entanglement, there's a phase transition from a connected phase to a disconnected phase. And this means that the entanglement entropy will stop growing at some certain time. It will saturate, both for environment and for the ordinary entanglement entropy. But the critical time where the saturation happens is for environment roughly proportional to the binding number. So you can probe this growth of the length of the wormhole, as it has been called. You can probe this for environment for a much longer time than for the ordinary entanglement entropy. But we also know from the basic definition that this binding number W is bounded from above. Namely, the long strands that we are considering can have length only, can have a length which must be smaller than this parameter n from the rank of the gauge group. So therefore also this binding number must be smaller than n. So we cannot probe arbitrarily close to the horizon or singularity. So this kind of has already the basic idea that entanglement with geometry breaks down close to the singularity is already kind of built into the setup. Then you can ask yourself, what happens to these order 1 corrections, which we are neglecting in this large n limit? How important are those? And that's why we've been studying 1 over n corrections to this. So 1 over n corrections for the ordinary entanglement entropy are, of course, already well studied. So there's a formula due to Faulkner-Lefkowitz and Mulder-Sena by quantum corrections to ordinary entanglement entropy, and then you can ask yourself, okay, can we relate to this formula somehow? And for that, we need to describe environment as a sort of ordinary entanglement entropy in some different theory. And that's what I'm going to try to convince you on that slide, that this is possible, although this Faulkner-Lefkowitz Mulder-Sena formula in that case will only be approximately 2. So more in detail, the degrees of freedom for environment that we are considering, they are located on a subset of all possible collections of long strands, as I told you previously. And this subset will form a subset of the Hilbert space, and then you can ask yourself, is there a quantum field theory that has exactly the same spectrum as the quantum field theory that we started with, but restricted to the subset? And it turns out there is such a quantum field theory. It is, again, a symmetric product orbifold, but of a different rank. So the rank is n divided by m. But the seed CFT is the same. And also, there's an important restriction. We are only allowing spins which are an integer multiple of this parameter n. So this is not exactly a symmetric product orbifold of the same CFT, but a symmetric product orbifold of the same CFT where we are projecting out some states. And you can rewrite this partition function here as the partition function which kind of looks like the partition function of a conformal field tree on a theory on a torus whose length is m times larger. So basically like the partition function at a different temperature or a different modular parameter. But there's a caveat here. What would ordinarily be multiplicity factors here, and that's positive, they can be negative in this rewriting. So this means that the environment will not be exactly an ordinary entanglement entropy in this Caroline theory, but we will have to take into account that this can be negative. So if you're just trying to compute entanglement entropy, this is not really a problem. But if you're naively applying this Lefkowitz Faulkner-Mulder-Sena formula, you have to take this into account. But otherwise, everything works the same. So formally, you can still use the version of this Lefkowitz-Mulder-Sena Faulkner formula in order to define 1 over n corrections. And then we are also interested in explicit results. So we did a direct computation for the BTC black hole using, again, large n techniques. So we can find explicitly 1 over n corrections. And here, yeah, this is the leading order, which is proportional to the length of a winding geodesic, as I told you previously. And then there are 1 over n corrections here. And you can ask yourself, well, how large are these 1 over n corrections? How good is the entanglement with geometry connection if you take into account non-zero winding numbers? And you find that the corrections increase roughly linearly with the winding number, but they decrease exponentially with this parameter n. So this means that if you are only looking at small binding numbers, which is where this formula is valid, then you will find that the quantum corrections are absolutely tiny, and the entanglement-based geometry connection seems to be very robust. It would of course be also very interesting to consider large binding numbers, which scale with this parameter n or scale with 1/2 Newton. However, in that case, you cannot get a universal result. Everything will depend on the details of exactly which C theory you are using. Everything will depend on the exact details of the UV completion, to say it in other words. But that's kind of what you would expect. If you get very close to a singularity, then everything will depend on the details of the field. Now, just very quickly, some comments. But what about exactly marginal deformations of the SN orbifold? So if you turn on some marginal deformation, of course the symmetric orbifold structure will be destroyed, but you will still have these subsectors of the Hilbert space corresponding to long strands. So you can still apply the same technique. You can still use this definition, even though your spectrum and the OPE coefficients will change. And that will, of course, also change this covering theory, which we have used to generalize the Faulkner-Lefkowitz medicine. And another comment is on the universality for these explicit computations that we did. So the formula that I showed you here is just the 1/n correction to the dominant conformal block. Depending on the details of the C theory, there might be further corrections to that. But here I'm only concentrating on the universal results. Now let me summarize since I'm out of time. So if you're looking at really understanding the connection between entanglement and geometry in ADS-CFT, you really have to take into account not only entanglement between spatial degrees of freedom, but also between different fields. I think this is the main message I want to convey in this talk. And for that, it's also interesting to consider 1/n corrections. And then the results that we have found is that there is an analog of the Faulkner-Lefkowitz-Metaxena formula. And another interesting thing is to consider obstructions to this by geometry reconstruction. And we find that for small binding numbers, there are no such obstructions, but generically they can appear if the binding number becomes very large and you get very close to a singularity or a horizon in space-time. And some open questions, which you can just read, and we can go to the questions. Thank you.
Okay, thanks for the nice talk. We have time for questions.
So I have two questions. One is about the saturation time of this environment. So I have some intuition of how it works for entanglement entropy, and I can associate saturation time with thermalization of the system. Do you have any intuition as to why this quantity seems to have a later saturation time?
So from the perspective, it's very easy to see this because you do have a competition between two phases. One phase is the disconnected phase, and the disconnected phase here is just two geodesics with non-zero winding number. And of course, the length of those geodesics will be larger than the length of geodesics of zero winding number, and that's why this phase transition happens at a later time. So that's just the intuition.
But you don't have any intuition from the quantum mechanics of thermalization that is behind this? Like, I understand the bulk story, but do you have any intuition in the field theory side?
Yeah, from the field theory side, I don't have a very good intuition why this happens. I would just say that perhaps if you look at more fine-grained measures of thermalization, then you will see that in these fine-grained notions, the system doesn't thermalize as fast as if you look at the entire system. That's kind of the intuition I can give you.
Thanks. The second question is, you may not have control in the CFT side, but using the holographic prescription, do you know how the story works for higher dimensions?
Well, that's one of the open questions. So there has not been any work on this kind of thing for higher dimensions, and it would really be very interesting to find out.
Yeah, thank you.
Not known.
Any more questions? I'm curious, do you, below the black hole threshold, when you don't have a black hole anymore in the block, does entanglement entropy suddenly become regular entanglement entropy again, does anything happen?
So the bike dual to the environment in that case is just an ordinary geodesic. So, of course, if you are below the Hawking page space transition point and you just have thermal ADS, there are no binding geodesics, and in that case, environment just becomes a binding geodesic. But of course, you're still computing a different quantity on the free geodesic. It's just that also the dual in that case is the length of an ordinary geodesic.
I see. Okay, thank you. Any more comments? Right, so thank you very much.